noodles going down in the middle of the day. I don't know why that was a good idea. So today we are moving on to the idea of nitrogen and nitrogen assimilation. And this is going to include eventually the formation of amino acids, and we'll start on amino acids today. And then the formation of nucleic acids, and we'll talk about nucleic acids. That'll be the PowerPoints that you guys will watch without me here next week. There should be 2 PowerPoints, and then on Friday we don't have class because of Good Friday, so there'll just be 2 PowerPoints. It should be the DNA and RNA metabolism, if I can get through amino acids this week. So we've talked about a couple of different pathways so far. We've talked about the assimilation of carbon and the carbon cycle, as essence you can call it, but what photosynthetic plants and bacteria do by fixing carbon into useful forms, so sugars, so the conversion of CO2 into a useful carbon source. So to us, CO2 is completely a waste product. It's completely nothing we can use functionally. So we can't incorporate CO2 into biologically functional carbon sources, right? The only organisms that can do that are the organisms that can go do photosynthesis. So they can fix carbon into a biologically useful form, ultimately will be glucose, that they can use, as well as we can eat those wonderful plants and other animals and use those useful carbon sources to make into things that we need in the cell. And we've gone through all the pathways of using glucose to make a lot of what we need for energy, etc. So now we're going to talk about the idea of bringing nitrogen into a biologically useful form. So obviously we need nitrogen for things in the cell. So all of our nucleic acids and proteins all have nitrogen components to them. So if you remember the kind of generic amino acid, the carboxyl and amino end, they all have nitrogen in them. Obviously all of your nucleic acids also have nitrogen, as well as some other biological molecules that need nitrogen, NAD, FAD, etc. Some hormones, pigments, etc. all need nitrogen. So we need to have nitrogen, just like carbon, into a biologically useful form that we can kind of incorporate into our different molecules in our cells. So our atmosphere is roughly about 80% nitrogen, N2, and that's the structure of N2. It's got that lovely triple bond there. But it's not a useful form. We can't use this form of nitrogen. It's chemically inert. We cannot bring it in. We need to convert it into a biologically useful form. Well, not us, because we can't do this. Just like we can't do photosynthesis, we can't do this either. So the delta G for breaking this triple bond is actually really highly negative. But unfortunately, it has high activation energy. So the ability to break that triple bond is very difficult to get over that activation energy. So there are a couple of non-biological processes, and not this general reaction, but a way to get atmospheric, so N2 nitrogen into a useful form. One of them is actually through lightning. So lightning has a actual function. It is able to convert nitrogen gas plus oxygen to NO. That doesn't obviously happen very often. We're not like continuously surrounded by nitrogen all the time. And then us wonderful humans have devised an industrial process to do this. So we can do it so nitrogen can be converted to ammonia via a process called the Haber process, and we'll talk a little bit more about that, not too much. But it requires very high temperatures and very high pressure in order to do that. So those are the 2 non-biological ways to convert atmospheric nitrogen into a biologically useful form of it. But bacteria can do it, just like everything else bacteria can do it. So some form of bacteria can do what we call fixing nitrogen. So just how we call this process fixing carbon, bacteria can also fix nitrogen. In other words, bringing atmospheric molecules and put them into biologically useful forms. Most of the organisms that can do this are single-celled prokaryotes in the archaea realm, or they live in symbiosis with either plants or animals. So there's a group of proteobacteria that live in legumes, and they're called rhizobia. You don't need to know that too. Right, it's just for your fun. That live in symbiosis with different legumes, and we'll talk about kind of how that partnership works after we talk about nitrogen fixation. Then there are a couple that live in symbiosis with animals. Some spirochetes live with termites, and they're able to do this process of fixing nitrogen into biologically useful forms. So they have enzymes that have this ability to overcome that high activation energy. I mentioned that to break that triple bond to nitrogen that has that high activation energy, they have some enzymes that are able to do this by hydrolyzing ATP, so using lots of ATP. Yeah?
I'm a little confused.
Mhm.
If it's exothermic and has like a negative delta G, how is there still it still needs the
It's the activation energy. Once the breaking of the bond is thermodynamically favorable, but in order to stabilize it, and I'll go through how the bacteria do it to stabilize that bond to be able to break it. And I'll show you how bacteria do. Maybe that'll make a little bit more sense after we go through fixation, because they do it. But it requires a lot of input to get that activation energy to get there. So let's talk, before we go into the actual process of nitrogen fixation, let's talk a little bit more about the nitrogen cycle. This may have been a slide that you saw sometime in your high school career. I'm sure you remember that really vividly, all these wonderful things. So this is the chemical transformations between the balance between N2, so atmospheric nitrogen and gas, and these biological useful forms of nitrogen, and this is called the nitrogen cycle. Part of the nitrogen cycle includes fixation. That's what we're going to talk about specifically. And that's when bacteria reduce this nitrogen gas to biologically useful forms of nitrogen, so fixing nitrogen. Nitrification, this is bacteria that can oxidize ammonia into nitrite and nitrate. Assimilation, so bringing that biological useful form and incorporating it into amino acids, etc., things that we need for the cell. Organisms will die and return some of this ammonia back to the soil. That ammonia will be converted to nitrate or nitrite. Okay? And then finally, denitrification. This is nitrite being reduced back to atmospheric nitrogen under aerobic conditions that bacteria can do. So this is the process of bringing the nitrogen in, putting it in its biological useful forms, making it into amino acids, or nucleic acids, etc., and how it gets back into the atmosphere, hence this cycle portion of the nitrogen cycle. So this is more like a cartoony version that you may have seen in one of your high school books, but here's our atmospheric nitrogen, the process of bringing it back into biological forms, that's nitrogen fixation, a little bit by lightning, but mostly natural biological fixation, into organic matter. So then the process of nitrification, assimilation into our wonderful consumers, that's us. One portion that we'll talk a little bit about at the end, and this is the commercial production of biologically useful nitrogen, and that is dumping our fertilizers on our fields. Okay? So bringing a man-made source of nitrogen into the cycle. Nitrogen also is deposited into the oceans, and this just gives you a detailed description of the producers and consumers that are involved in the nitrogen cycle within the ocean. But then ultimately, denitrification, the bacteria are able to bring the nitrogen back into the atmospheric nitrogen, completing the cycle. So the process of bringing atmospheric nitrogen into biologically useful forms, and most of this is all done by bacteria. It's incorporated into plants, we eat it, us and other animals, we eat those animals. They are brought back into the soil, they are denitrified back into atmospheric nitrogen. So to look at that more on a chemical scale,